Hello, I'm Grace Chen. I'm one of the product leads for ML frameworks.
And I'm Carlos, and I'm a product management lead supporting JAX.
Today, we're here to talk about the frameworks we have for generative AI. We'll show you how you can use Keras to adopt foundational models and how you can use JAX for the power of training your own models. Let's get started. We've had machine learning for some time with a wide array of use cases from traditional computer vision to recommender systems to now the latest and greatest is generative AI. Generative AI has captured everyone's imagination. There's always something different to inspire anyone and everyone. And today, I'm going to show you how you can take advantage of that. But first, let's take a quick look at our path to AI. Getting here has been a journey. Machine learning modeling has been around for a while, but with the release of TensorFlow as an open source framework, along with Transformer, it led to an explosion in innovative models, from Lambda to PaLM to now Gemini. It is a journey of growth, adaptation, and relentless innovation. As AI technology has evolved, we have also evolved the tools to build these technologies. The last year or two have brought remarkable breakthroughs with generative AI models. However, these gains come with the significant cost of training and serving massive models, far larger than ever before. This underscores the critical importance of scalability, efficiency, and optionality. Many industry experts predict that requirements will continue to grow 10 to 100 times the current level into the future. We're going to share what we have done to make it easier for you to take this revolution with the tools we provide to build these models or extend them. That is Keras and JAX that we'll talk about today. Keras is a multi-framework deep learning API. For most of you who are listening today, you probably want to get hands-on with pre-trained models. And I'll talk about how Keras provides fast and easy access to powerful pre-trained Gen AI models like Gemma. Then Carlos, my colleague, will talk about JAX, a powerful framework for large-scale training and research to develop foundational models and what we use at Google to build Gemini. First, let's start with Keras. We've been working really hard on Keras and adding a whole bunch of generative AI features. Starting with pre-trained models. Your generative AI journey will likely start by using models that other people have built before you get into building your own. With Keras, you can use things like Stable Diffusion or Gemma or other open models with just a few lines of code. Keras comes with two collections of state-of-the-art pre-trained models, Keras CV for computer vision models and Keras NLP for language models. You can browse the available models on Kaggle Models at kaggle.com/models. All the models work across supported backends, JAX, TensorFlow, or PyTorch, with clear and reusable Keras implementations. Let's talk about Gemma for NLP and generative text. It comes in a number of variants that are designed for different scenarios, such as small 2B parameter models or instruction-tuned ones. Keras makes it easier for you to use it in your code. As you can see here, loading a preset model in Keras requires only a single line of code. But wait, there's more. To effectively fine-tune large language models, which are memory-intensive, Keras provides specialized APIs. There's LoRA, low-rank adaptation. This is a technique that freezes the base LLM and introduces trainable parameters as a product of two low-rank matrices within each layer. This significantly reduces the number of trainable parameters, making fine-tuning more manageable. Then there's model parallelism. For LLMs too large to fit on a single accelerator, model parallelism allows the model to be distributed across multiple accelerators for both inference and training. Keras includes an API to facilitate this process. But let's not just do it in slides. Let me show you how to fine-tune Gemma using LoRA. Please note, you can run the demo yourself at the URL that appears at the top of the screen. We're running on a TPU with 8 cores, and the selected numerical backend for Keras here is JAX. First, I run a couple of setup cells. And here we load the model. Notice that we're loading the Instruct 7B variant. Instruction-tuned Gemma is better at following instructions and also understands turn-by-turn dialog tagging. This chat state helper is where the dialog turn tags are inserted. The helper, which you can copy-paste into your own chat implementations, also keeps track of the entire conversation. When chatting with an LLM, you have to feed the entire conversation back to the model at each turn. That is how LLMs can react to something said earlier. We will fine-tune this model to make it speak with a specific voice. Let's say like a pirate. Why not? But first, we must make it fit in memory. And we will use 2 techniques for that. First, we partition the large model across the 8 cores. We actually did that just before loading the model, using the Model Parallel API. For each large block of weights in the model, we specified how to split it and on which accelerators to put the pieces. I'm going to skip the details here. You can look it up in your Model Parallel guide. Then we enable LoRa to reduce the number of trainable parameters for fine-tuning. And finally, we use Model Fit, the built-in Keras trainer, to fine-tune the model on your Pirate Speak dataset. Notice the number of trainable weights. LoRa reduced it to only 22 million. The original model had 8.5 billion parameters. That is a LoRa technique that is working to reduce the number of trainable parameters. Now the training is in progress. I'll just wait for that to finish loading. And as you can see, the loss is decreasing nicely. Now we can start chatting with Gemma that is fine-tuned on our Pirate Speak dataset. Let's see if the model can speak pirate. Ahoy there. And it's answering, ahoy there, it's nice to hear from you. It is speaking pirate. The fine-tuning worked. What could we talk about with a pirate? Well, obviously, prime numbers. Yes, it worked. It's giving me a bunch of prime numbers. Now I want to see if this pirate can actually generate code in Python. Sure, here's a Python code. It wrote the code and it kept the pirate voice. To finish, let's see if this code can run. I'll copy-paste it into a new notebook cell and run. And yes, it's computing prime numbers. As you just saw, using an LLM like Gemma is easy with Keras, and LoRa fine-tuning was something I could do just in a few lines. And that was me doing it. If you have large-scale infra for GPU, TPU clusters on the backend, you can share the work across them with model parallelism. Of course, we're not just building Gen AI stuff with Keras. The platform has undergone tremendous updates to make it more powerful and flexible than ever. Let me go through a few, including the much requested backend optionality. So now you, as a Keras developer, you can use TensorFlow, PyTorch, or JAX as the backend. And as you can see, regardless of which backend you use, your code doesn't have to change. You can also develop custom components, layers, and even metrics using Keras apps, then deploy them across your research and production environments with any of the supported backends with very little effort. For example, NumPy is powerful, but doesn't have neural network-specific functions such as softmax, so we developed it for you in Keras. Keras is not just intended for Keras-centric workflows where you define a Keras model and call model fit. It's also meant to work seamlessly with low-level backend native workflows. You can take a Keras model or any other components, such as a loss or metric, and start using it in a JAX training loop, a TensorFlow training loop, or a PyTorch training loop, or as part of a JAX or PyTorch models with zero friction. Our seamless integration unlocks the full capabilities of your chosen framework. It is our way of maximizing your productivity and innovation. Thanks for listening. If you want to learn more about Keras, please check out our Keras I/O session, Large Language Models with Keras. And all the links here are available in the video description. While Keras makes it easy for you to use and adapt Gen AI models like Gemma, JAX is a powerful framework for large-scale Gen AI model development and what we use at Google to build Gemini. Now I'm going to turn it over to Carlos, who will talk about JAX.
Thanks, Grace. In the last section, we learned about how Keras makes it easy to use and adapt lightweight models like Gemma. But what do we use to develop models that are 10 times or 100 times larger than Gemma and other lightweight models? Models that require 10 or 15 trillion tokens to train or more. You've probably heard that these kinds of models can take months to train, so efficiency becomes hugely important to save time, cost, and enable you to iterate more rapidly. So if you want to build a large model of your own, wouldn't it be great to use the same framework that we use to train models like Gemini? Well, that's JAX. So what is JAX? At its core, JAX is a Python library for high-performance machine learning and numerical computing. It provides composable function transforms, like compilation so code runs more efficiently, and also transformations like auto-differentiation and vectorization, which make it easier to do machine learning. It also provides a NumPy API, so let's see how easy it is to get started. Here, we have a simple example using NumPy to define a predict function for a forward pass of a multi-layer perceptron, and also a function which calculates the squared loss. To turn this into JAX code, you simply import jax.numpy, and then you can replace the NumPy calls with calls to JAX. So that's pretty easy, but why would you want to do this? Well, JAX has some important benefits and is also part of an ecosystem that makes it really powerful. First, JAX was designed to be compiler-oriented, and it sits on top of XLA. This makes JAX really efficient on accelerators like GPUs and TPUs, both on a single chip and across many accelerators. JAX is also designed to be portable, so it's easy to move between CPUs, GPUs, and TPUs with zero or minimal code changes. That's part of what makes JAX blazing fast, and we'll get more into that later. But that's not all. An important principle of JAX is to focus on discrete, loosely coupled components, which can be easily interchanged. And so on top of JAX, there is a powerful ecosystem of components for machine learning. This includes Flax, a modeling library making it easy to develop models, Optax for optimizers, Orbax for model checkpointing and serialization, and the list goes on. The most recent addition to the ecosystem is Jetstream for optimized LLM serving. At the highest layer, we have reference implementations like MaxText for the most common models like Gemma, Llama 2, and more. And again, the ecosystem is designed to be modular, to facilitate maximum flexibility and enable you to develop your own components or use alternatives. A great example of this optionality and modularity is from the previous section on Keras, which now also supports JAX as a backend. Now that we've covered some of what JAX is and why it's great, let's dig a little deeper into two areas that are particularly important for Gen AI and large model development. Those are efficiency and scalability. So let's start with efficiency. First, we hear a lot of positive feedback from the community, not only on how fast JAX is, but also how easy it is to see those improvements. These two quotes really highlight this by speaking to the out-of-the-box performance you get with JAX, and also how much time you can save not writing so many custom kernels. This also enables researchers with no experience in high-performance environments to scale efficiently and without requiring deep domain expertise. Now you'll notice that both of these quotes mention JIT, and so let's talk about what that is. JIT is one of JAX's transformations, which takes in a function and compiles it. In compiling functions, it also looks for optimizations to make the code more efficient. And it uses several techniques, like fusing several operations together into one more efficient operation. So let's see it in action. In this example, we're running a micro-benchmark on an activation function which is commonly used in deep learning. First, we define the function, in this case, a cello activation function. Then we create a tensor with 1,000,000 values. And finally, we do a micro-benchmark of that function on the tensor. When we run it, the benchmark is 2.05 milliseconds per loop. Now, to compile the function, we simply call jax.jit on the celu function, and that returns a reference to the compiled version. You'll notice that we run the function once before the micro-benchmark. This is because on this first execution is when JAX will actually trace and compile it. Now when we run the new benchmark, you'll see that it ran in just 150 microseconds per loop, which is 13 times faster than the previous example. That's incredible. It's also important to highlight that JIT also supports automatically parallelizing and optimizing distributed computations. That's important for scale and how JAX can easily scale to thousands or tens of thousands of accelerators. And this leads us to our next benefit, scalability. As this quote highlights, one major reason developers switch to JAX is its modern approach to parallelism, which really facilitates scaling efficiently while handling a lot of the complexity for you. We can also push these capabilities to massive scale. And in this example, we show that the largest public training job of 2023 leveraged over 50,000 TPUs and was done with max text using JAX. It also shows that JAX achieved state-of-the-art efficiency across a wide spectrum of scale. The way we achieve that scale, but also even in cases with a handful of GPUs, is by using different techniques which allow you to use infrastructure in parallel, and thus efficiently. JAX enables this through parallelism APIs that give you a lot of control and flexibility while also handling a lot of the complexity for you. So what are some of these parallelism techniques that we use? To demonstrate, we'll discuss two techniques using 4 accelerators and how you would develop them in JAX. First, we'll cover distributed data parallelism. In this technique, you replicate a model across 4 accelerators, meaning that each accelerator has a copy of the same model. Then you shard the data across the 4 accelerators, meaning that each accelerator has a different chunk of data. By doing this, we can train the model on different data in parallel, and the model will share parameter updates across the devices to stay in sync. The second technique is called fully sharded data parallelism. And in this technique, you are sharding the model, meaning that the different parts of the model reside on different accelerators. And then you are also sharding the data, as you did with the first technique. So these are 2 different ways of parallelizing execution across these accelerators. So how would you do this in JAX? In JAX, we have the concept of a mesh, which allows you to arrange accelerators into an n-dimensional array with named dimensions, and in this case, a single dimension containing 4 accelerators, and we name that single dimension batch. Then to place the data and the model parameters properly on the mesh, you shard the data across the batch dimension of the mesh, which puts different chunks of data on each accelerator. Finally, for the model params, since you are not sharding the model, you are replicating it, you leave the partition spec empty. So that's for distributed data parallelism. Now to switch to being fully sharded data parallel, all you need to do is change the partition spec for the model params. In this case, you want to shard the model params, and in particular, the second dimension of the model params, since you want to shard by the columns, not the rows. So you set the first dimension, the rows, to none, and then set the second dimension to batch so that the columns are the sharded dimension. And that's it. From here, and with more accelerators, you could create different meshes and try different parallelism techniques quite easily, and also with limited effects on other modeling code. This is just one example of what makes JAX easy and efficient to scale. So that was a look at just a few of the things that makes JAX a powerful tool for large-scale Gen AI model development and research, and we hope you give it a try. Please visit our resources for JAX and other components to learn more. Thank you for your time.